Welcome to General Chemistry Mini Lecture Series, Lecture 30, Hess Law. Many chemical reactions can be expressed as multi-steps. So if that's the case, the total enthalpy change for the reaction is actually the sum of the enthalpy changes for each step. So this way, we should be able to use the enthalpy of the individual steps to find out the enthalpy of a reaction for that given reaction. Now let's take a look at this hypothetical reaction. I call that desired reaction or the overall reaction. That should be the sum of two individual reactions. This reaction number 1, individual reaction number 2. For reaction number 1, reactants W and 2x, product Y. So that's reaction number 1. Reaction number 2, the reactant is Y. Start from Y to the product 2Z. The enthalpy change of this reaction is positive 45 kilojoules. Okay. If you recall, delta H with a negative sign, that means exothermic. Positive sign, endothermic. Okay. Reaction 1, that's an exothermic. Energy is released. That's a higher energy, that's lower energy. And for reaction 2, energy is added. Now, if we add the two individual reactions, we should be able to obtain the desired reaction, the sum of the two individual reactions. In other words, if you add them up, you will end up with the desired reaction. The practical way to do this is you just start with reaction 1, start with all of the reactants, or on the left-hand side, everything on the left-hand side, W plus 2x, then plus Y. But if you look at that, after the reaction, you have another Y there, so therefore those two Y's are cancelled. Then you have this arrow sign. Then on the right-hand side of the arrow sign, you just have 2Z left, so which is a product. And this reaction is exactly the desired reaction, or the overall reaction. But in Hess law, you don't just add up the reactions. You have to do the same for the delta H. So therefore, delta H of this desired reaction, that should be the sum of the two, which is negative 55 kilojoules. That means it's an exothermic reaction. It is this reaction from W reacting with 2x forming 2Z. So that's negative 55 kilojoules. So this basically how you apply Hess law in calculating the delta H of reaction or heat of reaction. Let's go over very briefly the guidelines when you use Hess law. So first, you want to rearrange those individual reactions, the ones normally with, of course, known delta H values. So when you add up those individual reactions, the sum should equal to the desired reactions or the overall reactions, which means it's the one with the unknown delta H of reaction. Okay, that's your overall strategy. You rearrange the individual reactions or the individual reaction equations. Okay, when you do the rearrangement, two things you need to pay attention. When a reaction equation is multiplied by a factor, you have to do the same for delta H. For example, for this first reaction, delta H is negative 393.5 kilojoules. But if you multiply the first reaction by 2, C becomes 2C, O2 becomes 2O2, CO2 becomes 2CO2, then you have to do the same for the delta H. The delta H value for the first reaction has to be multiplied by 2. So therefore, the delta H for the second reaction is negative 787 kilojoules. Sometimes you need to reverse a reaction. If you do that, the sign of that delta H must be changed. Look at this reaction. Carbon reacting with oxygen forming carbon dioxide. And this is exactly the reverse reaction of that one. The delta H for this combustion reaction, that is negative 393.5 kilojoules. And the delta H for the reverse reaction has to be positive, the same value, 393.5 kilojoules. When sum up the individual equations, make sure you cancel the spectator species like what I just did in the previous slide, canceling the y's. All right? And most importantly, you have to add the delta H values of all of those individual reactions. Let's work on one example. Carbon disulfide can be processed by reacting graphite with rhombic, according to this reaction. This is the overall reaction or desired reaction with an unknown value of delta H. And our job here is to find out what delta H is using Hess law. Then, of course, we have to know the information of those individual reaction equations. Okay? So how do we do that? We follow those guidelines talked about in the previous slide. We have to rearrange those individual equations if necessary. Okay? So first, let's take a look at equation number 1. Graphite reacting with oxygen, always compare each individual reaction with the overall reaction. Graphite, they are found on the same side of those two reactions. And the coefficient for graphite, for carbon is 1 and 1. So therefore, we don't need to do anything for equation 1. We just simply copy equation 1. Okay? Now, let's take a look at equation 2. Sulfur, or rhombic, reacting with oxygen. And then rhombic is also found on the left-hand side in the overall reaction. So therefore, we don't need to change the direction of equation 2. However, here in the desired reaction, that's 2s, and here is just 1s. So therefore, what should we do when we modify equation 2, or how should we modify equation 2? We need to multiply equation 2 by a factor of 2. Okay? So 1s becomes 2s, and so on and so forth. Then we have to multiply the delta H of equation 2 also by 2. You see, negative 296.1 multiplied by 2 becomes negative 592.2 kilojoules. So this becomes a new equation. It is actually equation 2, but we modify the equation 2. Now it becomes equation 4. Let's take a look at equation 3 then. Equation 3, carbon disulfide on the left-hand side, but in the desired or overall reaction is on the right-hand side. Oh, we know we need to reverse this reaction. Okay, so we just simply reverse reaction 3. Okay, but when we do that, we have to make sure we change the sign of delta H for reaction 3. So therefore, negative 1072 kilojoules becomes positive 1072 kilojoules. And this new equation, modified from equation 3, is number 5. So now instead of sum up equations 1 through 3, we are going to add equation 1, equation 4, and equation 5 together. Okay? So then if you do that, you cancel the spectator species, and this should what? Be left. Carbon plus 2 sulfur, and then you have carbon disulfide on the right hand side. Okay, so you can practice this by yourself, just a simple math, chemistry math. So don't forget, you need to add up all of those delta H values. We need to add delta H1, delta H4, delta H5, add them together, and then the delta H for this overall reaction is 86.3 kilojoules. Now problem is solved. Let's take a look at another example. So we want to use those information to find out the delta H of reaction for this desired reaction. Okay? Let's do the same, applying Hess law. How to apply Hess law? We need to rearrange those individual equations. Okay? So if needed, change the direction of a reaction, and then of course also change the sign of the delta H value. Let's take a look at the first reaction. Iron reacting with oxygen, forming iron 3 oxide. And then in the desired reaction, iron is on the right hand side, not on the left hand side. That's why we need to reverse equation 1. When we do that, we need to change the sign of delta H1. Okay, so therefore delta H3 should be positive, while delta H1 is negative. Okay, the value is the same. The numerical value is the same, but the sign has to be changed. Now look at equation 2. Carbon monoxide is on the left hand side. All right, then carbon monoxide is also on the left hand side in the overall reaction. But what do we need to do with the equation 2 in order to apply the Hess law to solve this question? We need to take care of the coefficient. So we need to multiply equation 2 by 3. If needed, multiply both equation and delta H by the same factor. Okay, so equation 2 we need to multiply by 3, but do the same for delta H value. So that's why delta H4 is 3 times of delta H2. Now we are ready to sum up the individual equations by canceling the spectator species. Then we obtain the desired reaction, the one with unknown delta H values. But now this unknown delta H value can be obtained by adding the delta H of the individual reactions. The answer for this question is negative 23.9 kilojoules. In other words, negative 23.9 kilojoules is delta H of a reaction for the desired or overall reaction. These are end of lecture 30 quiz questions. I will see you guys in lecture 31.